So now let's have a look at some of the neuron level mechanisms that support the column mechanisms. As we discussed for semantic memory, at the neuron level there's a need for multiple receptive fields. For example, consider a neuron in this discriminates visual objects area. The area gets inputs from areas closer to sensory inputs, from areas encouraging activity on the basis of frequent past activity at the same time, and from areas prolonging activity. But what you don't want is activation in this target area resulting from a combination of weak inputs from all three areas at the same time. Now earlier we discussed the segregation of the receptive fields supporting direct and indirect activation. So if there is a further requirement for activity prolongation, a further segregated receptive field is necessary, perhaps located on the proximal apical dendrites, the region of the apical dendrite that's close to the soma. Anatomically, in the cortex, basal dendrites tend to be confined to one or a small number of layers, while the trunk of the apical dendrite extends through multiple layers. The axons from one source area tend to be confined to one or a limited number of layers. However, for this to work, there needs to be some additional management. For example, to prevent inappropriate activation on the basis of a combination of relatively weak distal apical inputs and relatively weak proximal apical inputs, there could be interneurons that get inputs from the activity prolongation signals and block the distal apical dendrites from contributing to neuron firing. So then, if there's a lot of input recommending activity prolongation, only pyramidals with a lot of such input are activated. Indirect activation input isn't allowed to contribute. But once again, the blocking mechanism will just be within the appropriate modulation time slot, and it must be pure blocking, not shifting the modulation, perhaps using a different type of GABA receptor. And the GABA B receptor does appear to be predominantly distributed on the distal apical dendrites. Now let's go deeper and have a quick look at how synaptic properties determine some of the working memory limits. If subjects are tested on a range of word lists of different lengths, where it's attempted to pick the words so that none of the words on one list have related meanings, then on average subjects recall 4 or 5 words per list. However, it's quite hard to avoid possible meaningful connections between words. All sorts of associations may have been created by the past experiences of the subject. So a better test is to measure recall for different lengths of list and measure the longest list length that can always be recalled without errors. And this turns out to be 3 or perhaps 4, depending on the subject. So this is a better measure of the raw capacity of working memory, because any semantic connections between words will tend to increase the number, and the minimum number probably reflects the capacity when there's no semantic connection, when there's no chunking. With chunking, recall can be 16 words or more. We can generally exactly recall a sentence that's just been spoken. But with larger groups, like multiple sentences, the exact words are not always fully remembered. The other important limit is that if a subject's asked to remember 3 words or consonants, but immediately given a verbal task to perform, the 3 consonants are only retained for about 5 seconds. So the question is, why do these limits exist? To understand them, we need to go down to neuron and synaptic properties. And we've covered a lot of this ground earlier in the course. Let me briefly remind you that an incoming action potential results in the injection of a postsynaptic potential, which rises to a peak in about a millisecond and decays away with a time constant of about 8 milliseconds. The postsynaptic potential from one synapse and one action potential aren't enough to reach the threshold for transmission of potential towards the soma. If multiple spikes arrive on the same dendritic branch, each will inject postsynaptic potential in proportion to the weight of the target synapse. And if one spike arrives before the effect of another has decayed, they can reinforce each other to exceed the threshold. So the threshold can be reached only if enough spikes arrive within an integration window that's of the order of the postsynaptic potential decay time. So if we divide up the output generation capability of a set of neurons into a succession of 8 millisecond time slots, then if all the spikes occur in just the first, fourth, seventh time slots, and so on, in all the time slots colored pink, then the effect on the targets of these neurons will be substantial. But if other neurons with the same targets produce spikes in green time slots, the effect of these spikes will be substantial, but relatively independent of the effects of the spikes in the pink time slots. And another independent spike population could also be supported in the grey time slots. To force spikes into one of the three time slots requires a modulation signal with a specific frequency. And a modulation signal with the same frequency but different phase is needed to force spikes into the green time slots. And to support all three sets of time slots, the peak-to-peak interval of the modulation signal must be at least 24 milliseconds, which translates into a frequency of about 42 Hz. And this 42 Hz falls into the gamma band observed in the EEG, which peaks close to 40 Hz. So a 40 Hz signal allows three 8 millisecond time slots. A 30 Hz signal would allow 4 time slots, and a 60 Hz signal only 2 time slots. So the observed maximum working memory capacity of 304 can be understood as resulting from an 8 millisecond postsynaptic potential decay time and a gamma band modulation. We can also understand time limits on our ability to recall 3 items when there's a distracting task in terms of synaptic properties. It's going to depend on reactivation of the items after their column populations have been extinguished by the distracting task. Initially, you've got 3 active column populations in some cortical area, corresponding with the 3 consonants, say. Those 3 populations have predominant recommendation strengths in favor of speaking the 3 consonants. But if a distracting task results in those active 3 column populations being replaced by other populations, how can you get them back? Remember, we talked about prolonging the activity of one area by developing short-term receptive fields in another area. But the activations in one area maintain the activations in the other, and vice versa. So a distracting task would extinguish the population in both areas, leaving nothing to drive a reactivation. However, if there was a third area that could prolong the activity in the middle area, developing the appropriate short-term receptive fields, then the distracting task might eliminate the original populations, but the receptive fields and activity to reactivate the populations is being maintained. So you can get the 3 populations back again, with recommendation strengths in favor of speaking the consonants. But remember, the synaptic weights are created by augmentation and decay in 5 or 10 seconds. So the period in which recall in this test remains possible can be understood as reflecting the timescale for decay of synaptic augmentation. Augmentation results from a short-term increase in the amount of neurotransmitter that's released in response to one incoming action potential. Several incoming action potentials in quick succession increase the amount of neurotransmitter that's released by the later action potentials, with the effect lasting a few seconds. So this somewhat different synaptic mechanism allows the support of the working memory phenomenon we've been calling short-term forgetting. So, having looked at the synaptic mechanisms, let's go back up to a higher level and discuss how there could be alternative ways, alternative sequences of processes which could achieve similar cognitive results, a point I mentioned earlier, so we'll go back to that in the next section.